Example 25. So this is example is on page 144. A single-cylinder four-stroke petrol engine working on auto cycle has a volumetric compression ratio of 8.5. So the volumetric ratio is symbolized by R, which is the ratio between the volume before compression and the volume after compression. So the polytropic index for compression here is 1.4. Brake power of the engine at 2000 revolutions per minute is 11.2 kilowatts with a mechanical efficiency of 83%. The cylinder diameter and the stroke are equal, and the indicated mean effective pressure is 620 kilopascal. The pressure at the start of compression stroke is 90 kilopascal. Calculate the indicated power in kilowatts, the work done in joules per cycle, the piston diameter in millimeter, the volume in cubic meter, and the pressure in kilopascal at all the main points in the cycle. Okay, first we're gonna need to draw the PV diagram of the problem. In the y-axis we have the pressure in kilopascal and the volume in the x-axis. So because we have an Otto cycle, so we have the first points that mark the beginning of the compression process. So we have one here. From 1 to 2 we have the compression process, and from 2 to 3 we have the combustion process. From 3 to 4 we have an expansion process, and then from 4 to 1 we have the exhaust phase. So now we are given R, which is equal to 8.5 to 1. So R represents V1 over V2. So which is 8.5. So we also have the brake power of the engine. The mechanical efficiency. So you know what the mechanical efficiency is. So it's the ratio between the brake power and the indicated power. The cylinder diameter and stroke are equal, so D is equal to L. So we are also given the mean effective pressure. So the mean effective pressure is the pressure that is considered to be constant. So we are assuming that the pressure in the engine was constant. So the pressure at the start of the compression stroke is 90 kilopascal. So that represents P1. So one cannot see the mean pressure on the curve. In order to know what the mean pressure is, we need to represent another PV diagram if you want to understand well the mean pressure. So we need to transform this graph into a rectangular shape. So we have P and V. So the mean pressure is, so here we need to extend all the way down. So that is called mean effective pressure. So the mean effective pressure is basically seen on a PV diagram. So if we assume that the area of the first diagram is the same as the area of the second diagram, and then we can determine that the pressure, because as you can see here, that is a rectangular shape. For a rectangular shape, the work done represents the area inside the curve. So that area can be calculated if knowing the length and the width. So the length represents the stroke volume and the width represents the effective pressure. So having P1 and the volumetric ratio, we can determine P2. We are going to use this relation here. P1 V1 to the power of n is equal to P2 V2 to the power of n. So we need to get P2. To get P2, I need to divide both sides by V1 to the power of n. So we also do the same here. And then on this side we can simplify these two. In fact, we need to determine P2. So to get P2, we need to divide both sides by this value here. So that when I simplify, I'm gonna remain with P2. So I'm gonna say P2 is equal to, I need to consider the expression on the left hand side. So I have P1 V1 n over V2 n. I can write this expression as P1 multiplied by V1 over V2 to the power of n. So now I just need to replace, because I know that this represents the volumetric ratio. So P2 will be, I have the value of P1, which is 90 multiplied by, so this represents the volumetric ratio, n, which is equal to 1.4. So if I compute this, I'm gonna get so I have 90 multiplied by 8.5 to the power of 1.4. So I have 1800.6 kilopascal. So I'm gonna write this on the new slide. So in question A, they want us to determine the indicated power. So that's supposed to be in kilowatt. So we know that the mechanical efficiency is given by the brake power divided by indicated power. So indicated power is symbolized by IP. So we can get IP. So if we do the cross multiplication, so we have IP multiplied by the mechanical efficiency, which is equal to the brake power. So to get IP, I'm gonna need to divide both sides by the mechanical efficiency. So when I simplify, I get IP, which is BP divided by the mechanical efficiency. So I have the brake power already, which is 11.2 kilowatt. So I have 11.2 divided by the mechanical efficiency is 0.83. So I get 13.49 kilowatts. So that represents the indicated power. And then they want us to determine the work done in joule per cycle. So to determine the work done, I have there are many possibilities to determine the work done, but we need to choose the one the possibility that work. So in order to determine the work done, the work done is the difference between the heat supplied to the engine minus the heat rejected from the engine. But to get the heat supply, I need to get these 2 points. So I cannot easily get these 2 points. I can get that one, but the property of this point cannot be determined because they are not enough that I can use to calculate Q in as well as Q out. But I also know that so in question B, they want us to determine the work done in joule per cycle. Okay, the work done can be determined from the well-known formula. So the formula to use is IP is equal to plan over 60. So now, from this relation, we can say that there is a possibility to figure out what the work done is. Okay, if I write again this formula, so I've indicated power which is given by P L A N E divided by 60. So in this relation, the work done can be seen here. The work done per cycle is all this. So the work done per cycle is all this. So take everything except N and 60. Because if we have the work done, we multiply by N, we get the power, because N is the rotational speed which is expressed in revolution per minute. We can also express it in revolution per second, but in this case we don't need to divide by 60. So if we have, because the power is just the rate of the work done, so it means it's the work done divided by the time. So where that time came from? The time came from the rotational speed, because the rotational speed is expressed in revolution per minute or revolution per second. So if we multiply the work done with N, we get the power. So all this represent the work done per cycle. So in other words, we can say that IP is equal to work done, which is denoted by W D multiplied by N over 60. So now that N depends. So if we have For a 4-stroke engine, N is given by the rotational speed RPM divided by 2. So that is used for a 4-stroke engine. But for a 2-stroke engine, N is equal to, so just use the RPM. But for a double-acting engine, N is equal to 2 times the RPM value. So make sure that you understand this rule correctly. So that is used for a 4-stroke. So that is 2-stroke. And this one is used for a double-acting engine. So we need to consider the first scenario. So now from this relation I can determine W because I have I've already determined the indicated power, and I know I can find the value of N. So don't take directly the N that is given from the problem. So you first need to apply these 3 scenarios. So you first need to consider these 3 scenarios. So in this case, we need to use the first scenario because we have a 4-stroke engine. For a 4-stroke engine, to get that N, we need to take the RPM which is given in the problem and divide it by 2. So in other words, we are going to say IP is equal to WD multiplied by, so in this case N will be that values divided by 2, so we need to put 1000 on top, and then we have 60. So now we need to make W subject of formula, so WD. So to do that, we can just use a simple cross multiplication. So if we multiply these two, we get 1000 is equal to 1000 multiplied by W is equal to IP multiplied by 60. So I'm gonna work out this on this space here. So I have 1000 WD is equal to IP multiplied by 60. So therefore, to get WD, I have IP multiplied by 60 divided by 1000. I've already determined IP, which is 13.5. So I need to multiply this by 60 and then divided by 1000. So I get, so the work done is 0.81 kilojoule per cycle, but they want me to express that in joule, so I need to multiply the value by 1000. So I get 810 kilojoule per cycle. That's it. So So now we're going to do question C. We're going to create a new slide for that. So in question D, we need to find the piston diameter in millimeter. So how can we determine the diameter? In order to determine the diameter, we need to have the stroke and the volume. We know that the work done per cycle is given by the plane equation. So I'm going to use this one, divided by 60. So here we can determine the volume. But if we look at these two, the product of the stroke and the area gives, so they give the volume. So LA represents the volume, and which volume? So that volume is called swept volume, symbolized by Vs. So in other words, we can say that the work done per cycle is equal to this represents the indicated power. This is the relation of the indicated power, not the work done per cycle. So if we have already determined the work done per cycle, then we will be able to find the volume. The work done per cycle is given by the mean pressure multiplied by the swept volume. So this relation came from the expression used to determine the area of a rectangle. Because if we have a PV diagram, we have the area inside the rectangle, which represents the work done, and this length represents the swept volume, and the vertical length represents the mean effective pressure, symbolized by P mean. So if we multiply the two sides of a rectangle, we get the area. So that area is the work done. So another way, the work done is given by the swept volume multiplied by the mean pressure. So this is where the relation came from. So remember that when dealing with a mean effective pressure, we need to consider a rectangular shape. We don't need to consider that shape because we only need a graph where we have one pressure. But if you look at this one, we have different pressure at all the corners. But all of them, these two graphs, they are similar in that fact that they have the same area. So the area inside that shape is the same as the area of inside this graph. But I can't use this one because I only need one pressure. So now from this relation I can determine Vs. So I'm gonna say Vs. So to get Vs, I'm gonna need to bring P mean to the other side, and it's gonna divide the the left hand side. So I'm gonna say Vs is equal to the work done. So this is the work done per cycle divided by the mean pressure. So I have already determined the work done from in the previous slide. So I got 110 kilojoule, 110 joule per cycle. So that's supposed to be in joule per cycle. So we say that the work done is given by the mean pressure multiplied by Vs. Then we can determine Vs from this relation. If we make Vs subject of formula, it's gonna be the work done divided by the mean effective pressure. So the mean effective pressure is given, which is 620 kilopascal, and the work done was determined from the previous slide. So we got 810 joule. So if we use the kilojoule, we're going to have 810. So I have Vs, which is, if I compute, I'm gonna get 0.810 divided by 620. So I got 0.001306. So the answer is in cubic meter. So that is Vs. Vs is the swept volume. It's basically the length of the rectangle. So now we are going to create a new slide to continue with question C. So we know that the swept volume, so here the objective is to determine the piston diameter. But in order to determine the diameter, we first need to know what the volume is. So the volume that we must use is the swept volume, so which is given by the stroke multiplied by the area. So that can also be written as Vs is equal to stroke length multiplied by, so we can write the area, so write the area of the piston in terms of its diameter, pi multiplied by d squared over 4. So now, if you read properly the question, it is specified that the diameter and the stroke have the same value. So in other words, I can also say Vs is equal to d. I can replace that one by d since they have the same value, multiplied by pi multiplied by d squared over 4. So now if I multiply these two, I get d cube. So I can say Vs is equal to pi multiplied by d cube to the power 4. So the objective is to make d subject of formula. To do that, we are going to use the cross multiplication. So we multiply these two and these two as well. So we get 4 multiplied by Vs is equal to pi d cube. So now to get d cube, I will send pi to the other side, or I'm gonna divide both sides by pi so that I can simplify. I only remain with d cube. So therefore d is equal to d is equal to cubic root of 4 multiplied by Vs divided by pi. So I now replace, I have already Vs, I've determined it from the previous slide. So Vs is 0.001306. So I've determined that value in the previous slide, and then I divide by pi. So if I work this out, I'm gonna get the diameter. So I'm gonna create a new slide for that. So we say that Vs is equal to area multiplied by, so that is the area of the piston multiplied by the stroke length. So the area of the piston is given by pi d square over 4, and then since the stroke is the same as the diameter as it is specified in the question, because there is a sentence here that said the cylinder diameter and the stroke are equal. So we can replace L by D. So now this expression simplified to pi d cube divided by 4. So that is Vs. So we can make this subject of formula. So if we do the cross multiplication here, so we have pi d cube is equal to 4 Vs. D cube will be 4 Vs divided by pi, and then D will be the cubic root of 4 multiplied by Vs over pi. So I've already determined the swept volume. So the value of the swept volume is 0.001306, and then we have pi. So if I work this out, So you need to use the cubic root 4 multiplied by 0.001306 divided by pi. So I end up with the diameter, which is 0.11847 meter. So that is equal to 118.5 approximately millimeter. So that is the So now we are doing question D. In question D, they want us to determine the volumes in cubic meter and the pressure in kilopascal at all the main points. So now we need to consider this diagram here. So we have P1, which is equal to 90 kilopascal. We also have the compression ratio, so which is symbolized by R. So R is equal to V1 over V2. So now I need to get P2. So to get P2, I'm gonna use the polytropic expression of this process. So I need to use the relation that combines the pressure and the volume. So if I say P1 V1 over N to the power of N is equal to P2 V2 to the power of N. So now I can write V1 and V2 in terms of the compression ratio. So I can determine P2. To determine P2, I'm gonna divide both sides by V2 to the power of N. So I do the same here, and then I can simplify. So I can say P2 is equal to P1 multiplied by V1 to the power of N over V2 to the power of N. So that can also be written as P1 multiplied by V1 over V2 to the power of N. So now I know what V1 over V2 is. So that is simply equal to the compression ratio. So I can say P2 is equal to P1 multiplied by R to the power of N. So P1 is N, and the compression ratio is 8.5. N is 1.4. Okay, let me just double check. Yeah, N is 1.4 for both the compression process and the expansion process. So P2 is equal to kilopascal. So that is the value of P2. So we have P1 and P2. So we are sorted for this process. So we have P1 and P2. So now we need to consider. Okay, let's first create a new slide. So now how can we determine the volume 1 and the volume at 2? So it's very simple. So we can say that we can use the expression of the work done and the mean pressure. So if we say the work done is equal to the mean pressure multiplied by the swept volume, so that is also equal to V mean. So we can write the expression of swept volume. Swept volume is just the difference between V1 and V2. So all this represents the swept volume. So now what I'm gonna do here is, so I have my first equation. I have the value of WD, which is, so I've determined it already. So I got 0.810. I also have the mean pressure, which is 620 kilopascal. So now here I have V1 minus V2. I don't have V1 minus V2, so I'm gonna call that equation 1. So I need to find the second equation that expresses V1 in terms of V2. So the second equation is R, because in R I can see there is a presence of V1 and V2, because I know that R is equal to V1 over V2. So here I can replace R by its value, so which is 8.5. So that is my second equation. So now I need to solve this simultaneous equation, so that I can see that we have two equations with two unknowns. The unknowns are V1 and V2. So how to solve it? I can make V2 subject of formula of V1. Okay, let me make V1 subject of formula from the second equation. So I can say V2 is so I can say V1 is equal to, so I need to bring V2 to the other side, so I'm gonna get 8.5 V2. So now I need to substitute, so I need to replace the expression of V1, which is 8.5 V2, into the first equation. So this is the first equation, so it means I need to replace this value by that one. So equation 1 becomes, so I first copy the right hand side, and then I say it's equal to 620 multiplied by, so that is V1. V1 is 8.5 V2, and then minus V2. So I need to do that on the new slide. So I'm gonna create a new slide for that. So this is my first equation. So the first equation is written in terms of V2. So I'll just copy it, and so I'll just reproduce it on this new slide. So I have 0.810 is equal to 620 multiplied by 8.5 V2 minus V2. So these two gives me, because there is one in front of V2, so I just need to take 0.5 minus 1, so I'm gonna remain with 7.5. So I have 0.10 is equal to 620 multiplied by 7.5 V2. So that is the same as if I say 620 multiplied by 7.5 V2. So now to get V2, I'm gonna need to send these two values to the other side, to the left. So in other words, I'm gonna say 0.810 divided by 620 multiplied by 7.5, so that gives V2. So therefore V2 will be equal to, so I just need to work this out. So V2 is 0.0001748 V2 cubic meter. So that is V2. So if I have V2, I can also determine V1, because I know that V1 is equal to, I need to use this relation here. V1 is 8.5 V2. So that is V2. So I get 0.001481 cubic meter. So that is V1, and that is V2. I mean, that is V2 and that is V1. New slide. So the question is to determine the volume in cubic meter and the pressure in kilopascal at all the points, at all the main points. So we have V1 and V2, but V2 is the same as V3. So if we have the value of V2, automatically we also got V3. So same thing here, V1, same thing on this slide, because the process is isochoric means constant volume. So V1 is equal to V4. So we have already determined the value of V2 and V1 from these slides here. So I have V2, which is the same as V3, and then I have V1, which is the same as V4. So I have the pressure at 1, so P1 is equal to 90 kilopascal. And then I have the pressure, I've computed the pressure at 2. Okay, let me find the slide. So the pressure at 2 is this one. It was determined from the volumetric ratio and P1. So I got that one. So now we're gonna need to determine the pressure at 3 and at 4. So we can determine the pressure if we use the work done expression, because we know that the work done of the entire cycle in terms of the pressure and the volume is given by, so we need to consider the process from 1 to 1 first. So we are going to have P1 V1 minus P2 V2 divided by N minus 1. So that is the work done of the process from 1 to 2. But the work done of the process 2 to 3 is 0, because the transformation is isochoric. For isochoric process, the work done is always 0. So now from 3 to 4, we have another work done which is given by P3 V3 minus P4 V4 divided by N minus 1. So now V2 is the same as V3 and V1 is the same as V4. So we just need to replace. We have already determined the work done per cycle. So the work done per cycle computed was 0.810. So that is equal to, we have P1 which is 19 kilopascal, and V1 was determined from the previous slide. So that's V1, and then minus P2 which is, so that's P2, and V2 is 0.0000174, and then divided by N which is 1.4 minus 1. So I need to continue, I need to do the same for these parts here. So I need to say plus. I don't have P3 for now, I'm gonna leave it as it is, but I have V3 which is the same as V2. So V3 is also equal to 0.000174, and then V4 is the same as V1, but I don't have P4. I'm gonna leave it as it is. So V4 is the same as V1. So and then I need to divide this by 1.4 minus 1. So now if I work this out, the whole thing, so I can just represent that on the new slide. So if I work this out, okay, let's so I have on my right hand side 0.8110 is equal to, so if I go back, I first need to work this out. So if I type it, so 0.00148 minus 1800.64 multiplied by 0.0001174 divided by 1.4 minus 1. So all this expression gives negative 0. So I have this, and then I need to add the other part. So I need to add this part here. So I need to say P3 multiplied by V3. So here I'm gonna use V3, which is the same as V2. So V3 is how much? So we have this value. And then we have P4 multiplied by V1. P4 multiplied by V4, but V4 is the same as V1. So V1 is 0.00148. So I need to divide this by n minus 1. N minus 1 is 0.4. So now I can see that I have an equation with two unknown which are P3 and P4. So that is my first equation. I need to get another equation in which I can find P3 and P4 in order to solve the simultaneous equation. So the equation is, so if I say P3, okay, I'm gonna get my equation from this side here. So if I say P3 V3 to the power of n is equal to P4 V4 to the power of n. So this is a well-known expression. So now if I say that, if I send V3 to the other side, so I'm gonna have P3 over P4 is equal to V4 to the power of n. So I'm gonna send V3 to the power of n to the other side. So it becomes so it's gonna divide this side. So I can also write this expression as, so I have P3 over P4, which is equal to V4 over V3 to the power of n. So for an Otto cycle, we know that V1 is equal to V4 and V2 is the same as V3. So R is the ratio between V1 over and V2. So that is also the same as V4 over V3, because V1 is the same as V4 and V2 is the same as V3. So we can replace V4 over V3 with R. So we can say that P3 over P4 is equal to R multiplied by R to the power of N. So I then have the relation in which we have P3 and P4. So just say P3 over P4 is equal to, I have the value of R, which is 8.5, and then I have N, which is 1.4. So now I can determine P3 here. So to get P3, I'll just bring P4 to the other side. So I have P3 is equal to P4 multiplied by 8.5 to the power of 1.4. So finally, I've written P3 in terms of P4. So I can say P3 is equal to, if I work this out first, so I have 8.5 to the power of 1.4. So I get 20.007 multiplied by P4. So to get P3, I need to multiply P4 by 20.007. So that is my second equation, and that was my first equation. So now what I'm gonna do here is I'm gonna replace P3. I'm gonna replace P3 that is in equation 1 by this relation. So I will say, so I start from the beginning. So I have 0.810 is equal to negative 0.4502 plus P3 is given by 20.007 P4, and then I multiply it by that value here, 0.0000174 minus P4 multiplied by 0.00148 divided by so I need to divide this side only, 0.4. So that is P4 and that is P4. So that is 0.00148. So now I can simplify the whole thing. So I'm gonna have 0.810 is equal to negative 0.4502 plus, I'm gonna write all this into a single expression because we have the last term, which is P4. So I need to multiply these two, and then I divide by 0.4. So I have 20.007 multiplied by 0.000174 minus 0.00148 and then I need to divide by 0.4. So I'm gonna end up with 0.005003 P4. So now I can make P4 subject of formula. I'm gonna say therefore P4. So to get P4, I'm gonna send this element to the other side. It become positive, and then I'm gonna divide both sides by this coefficient. Okay, I'm gonna show it on the new slide. So that's the new slide. So the equation is this one. I'm gonna copy it on top. Okay, let me also remove all this. So the equation is 0.810 is equal to negative 0.4502 plus 0.005003 P4. So I can determine P4. I'll first send this to the other side. So I'm gonna have 0.810 plus, it become positive, and then I have plus 0.4502 is equal to 0. So it's equal to that one. So to get P4, I'm gonna divide both sides by the coefficient of P4, which is, so I need to do that on both sides, and then I can simplify. So if I work this out, I'm gonna get the value of P4. So I have P4 is equal to so I have 0.81 plus 0.4502 divided by 0.005003. So I get 251.88 kilopascal. So now to get P3, I'm gonna use the relation that we have written on the previous slide. You know that P3 is equal to, I'm referring to this relation here, 20.007 multiplied by P4. So that gives 20.007 multiplied by 251.88. So the value of P3 is 039.5 kilopascal. So that is P3. And that is P4. Okay, that's it. So in question D, we basically need to have 8 elements. So the pressure at 1 and the volume at 1, the pressure at 2 and its volume, the pressure at 3 and its volume, etc.